Section 10 is about another consequence of dispersion. When we say the dielectric constant is frequency dependent, there's a consequence of that, and that actually is quite important or quite drastic, and usually it's not intuitive, so you won't expect that just by the fact that the dielectric constant or the refractive index depends on frequency. And there's some very important consequence that we can actually derive from that. Just simple fact that is frequency dependent, but it takes some mathematics, some math to some derivation to show that. So basically, when we say that the dielectric constant is frequency dependent, so we have the displacement x that depends on x and omega. So just one Fourier mode omega, and that is related to electric field with a dielectric constant depends on omega multiplied by the electric field, and that also for that frequency. So this is what we mean by a dielectric constant. This is frequency dependent. So we have this relationship. Okay, and right now we are restricted to this epsilon that depends only on omega, and we'll see that this is in Fourier space or the frequency space. If we get to the real space that depends on x and t, we see that d will depend on not just E at the same instant, actually depends on the integration of E over time. So that is basically a property of the Fourier convolution. So if you have Fourier transform of two Fourier transform multiplied together and you do an inverse Fourier transform, you'll get a so-called convolution that depends on the integration over T of these, the combined property of the product of these two in the time domain. Okay, we see that right away. But just to mention that this is still a simplified version of a more general dielectric constant, because this epsilon only depends on omega, but in even more complicated cases, that the epsilon can also depends on the wave number or the wave vector. And in that case, the dependency of D and E in the physical space and X and T actually is an integration of both time and X. It means that it's a non-local in both time and space. So that can get to really complicated situation. And one more complication is this epsilon may not actually be there's a scalar quantity. It can be a tensor. Generally, it's a tensor. So this is a tensor dot into E instead of just a scalar multiplied by E. So there's still a couple of levels of complication, but we'll not see that in E&M. But maybe in particle physics, you will get to see an epsilon that depends on K and omega, and it's a tensor that in particle physics we have those situations. Okay, so let's just get to the consequence. So this is in Fourier space, and we can write down the in time domain. So basically, this is just a inverse. This is an inverse Fourier transform. So you just integrate, put dx omega here, put dx omega, but dx omega is just this one, right? And then multiply by the e to the minus I omega t and d omega. Okay, so that's just the inverse Fourier transform, but substitute this into the Fourier transform of d in here. Okay, and Like this is using the convention that we have a square of 2 pi, 1/2 pi as the coefficient. So both the forward and inverse Fourier transform have the same factor. And we have this minus I omega t as usual here, but when you get to the Fourier transform, we have I omega t. All right. So what we'll do is express this Fourier transform of E as a just as integral in T now, because E is also a Fourier transform. This Ex omega is a Fourier transform of Ext, so we can express that. So we can write that as so. For that one, for you to express it as a Fourier transform, then you have another 1/square of 2 pi. So you multiply the two together, you have 1/2 pi in front. And for the epsilon part, you keep the epsilon omega, and you keep e to the minus I omega t, d omega. But for the e, you change it to integrating e x. And normally it's x and t and integrate over t, but we already have a t here. So when you express it as integral in t, so that t actually should use another symbol like t pi. Okay, you integrate minus infinity to infinity, and you multiply by e to the I omega t pi dt pi. Okay, so that is just this part into the Fourier transform expression. Okay, now the idea is to get the convolution out. And to do that, we can, you can do the whole thing as a convolution, but in the discussion between E and D, usually we pull out a vacuum situation. In the vacuum, D is just epsilon 0 times E. Okay, so we add this term, right? Assuming like an electrostatic case, it's epsilon 0 times E in the vacuum, you get this one. So that is actually correct. If we just really have a vacuum with no medium, so that would be correct. But then all the medium information is in this epsilon. So we add this and subtract that. So basically, so the rest we need to subtract this one. So to do the subtraction, you can say multiply by epsilon 0 and divided by epsilon 0. There's a 2 pi. And so that's the first term, you have this epsilon omega divided by epsilon 0. So this multiplied by that, we'll recover this one. Okay. And then we minus 1. We're using this minus 1 term to cancel this term. We see that right away why this will cancel after we get all the rest of the integral written out. So you have minus I omega t. So this factor multiplied by this factor. So you have t minus t pi. Okay, so, and then you have a d omega. All right, and then the rest is integrating over. There's a t pi here, so I should put another integration over t pi. So run out of space here. So another t pi integration, but then you have the e x t pi dt pi. Okay, so t pi is the outer integration, including e in here. But this part doesn't, it depends on omega. So the inner integral, that only in the omega integration is just this part. Okay, So we are expressing that. So, and we'll see that why this, the -1 sign term will cancel this one, because -1, just consider this term. So you take d omega. So this part is an exponential function. When you do the omega integration, just this one, if you remember, we talked about this before. This is, when you do this integration, you get 2 pi times the delta function at t minus t pi. So you cancel 2 pi in the denominator. So it's just a delta function t minus t pi. When you do a dt pi integration, t pi changes to t. So this term will give you exactly this term with a minus sign. So this both of this cancel. So this will recover the previous equation. Okay, so that's a trick. And it's not necessary, just getting this extra term out that is just the vacuum situation. It means that for a medium, you have the second term, this double integral would be non-zero. But for vacuum, the whole thing will be zero. You recover just the vacuum relation. Okay, so that's up to here. And you see that this integral, we can give it another name because the rest doesn't depend on this integral. Okay, so that's what we will do on the next page. Any question up to here? There's just a little bit of manipulation with a Fourier transform. Any question up to here before we go to the next page? No. So now the rest of this expression, we can do just a transformation of integration variable to make it nicer. So this, we just copy what we have. So the vacuum term. Okay, and then the not writing, not string. I don't know what happened. All right, so, and the integral. So we, instead of the dt pi, now we change this, call t minus t pi as our tau. So the outer integration become d tau instead of dt pi. All right, and then you have 1/2 pi. The inner integration becomes you have this epsilon omega over epsilon 0 minus 1 e minus I omega tau. Tau is again t minus is t minus t pi. So this integral. So that's our inner integral. And you multiply by this e to the x. I mean, before it's t pi, but t, so let's just write t is t prime minus t is t pi minus t, right? No, t is t minus t pi. Tau is t minus t pi. So t pi is t minus tau. So you have t minus tau here. Doesn't have enough space. Okay, so just change the variable, just change from integrating over t pi to tau. Okay, so it's nothing compared with the last equation. What we did is just this one. Okay, but then this whole bracket, this bracket, we can define it as one function because the rest doesn't depend on this integral over omega. So the rest is just expressed as integration, and both are proportional to omega. I mean, proportional to epsilon 0. So you can group that two together and write it as d tau and write this bracket as our function g tau, and then the rest is e x t minus tau and b tau. Okay, so this is defined as g, so g is g function of tau is 1/2 pi, and you have epsilon omega of epsilon 0 minus 1 e to the minus I omega tau d omega. Okay, so this looks like a Fourier transform, right? This looks like or expressing g as a Fourier transform of this function, except this you have this 1/square of 2 pi instead of square of 2 pi. So, but otherwise, it's similar to a Fourier transform of this function. But anyway, so this is how we transform this into the g, and what we see is now d not just depends on e at this given time, the same time t. It actually depends on integration over the all time. Actually, it's just expressed as t minus tau, but tau up to here is integrating by minus omega to omega. So not just all the e at the same time t, but all the time before this time and after this time. So integrating the whole thing. So that's this expression. So it's d depends on the non-local, the value of e, non-local in time. So that's the consequence of when epsilon depends on omega, you have that consequence, because when epsilon depends on omega and it's not equal to omega 0, this g is not 0. So this second term is not 0. So it means you will depend on e for the whole range of time. So that kind of a drastic consequence. Okay, so, and this form is what we call in Fourier transform, we call this convolution. Okay, any question up to here, this derivation? Anyone have question? No, so let's just do a simple expression illustration. So if it's the previous situation like electrostatic epsilon is just a constant. So we see what a constant, if we substitute a constant in here, what you get from G. If epsilon is a constant, instead depends on omega. So then this square bracket is just a constant factor. You can pull it out of the integration. And the integration over omega will give you just 2 pi times delta function tau. So for epsilon omega equals epsilon equals to a constant, then g tau. This is a special case, or not quite realistic case, but just to show at least theoretically what could happen if we assume epsilon doesn't depend on omega, just a constant. Then you get g as a delta function. All right, so if you substitute this delta function into here and do the tau integration, then all you get is this factor, epsilon over epsilon 0 minus 1 times e evaluate exactly at x and t, evaluate at t. Okay, so that becomes local again. Okay, so and you combine with this, you just get the usual relation d is epsilon times e. Okay, so that you recover the electrostatic situation. Okay, so, but this is not a very realistic model for a medium. So we could use our previous model for a medium with a single molecule or single oscillator. Then This is in equation 7.51. We have a model for just a oscillator and a molecule. Just consider one term instead of multiple terms. Then the epsilon for that case, after the derivation, you get this written in this form, epsilon divided by epsilon 0 minus 1. If you use that equation, you get omega p squared over omega 0 squared minus omega squared minus I omega gamma omega. Gamma is the damping rate for the oscillator. Okay, so that's what we got before. Now, if you use this one and substitute into this integral, and you can calculate this, what this G tau is. G as a function of tau. So, and now it involves some complex integration, which I don't know if everyone has taken complex, have seen complex analysis. Everyone has taken math physics, right? Have you gone through chapter 11? I mean, I know the two of you know because I taught that. So, but the
one we haven't gone through that yet.
So math physics for this year, this is the second semester, right?
Mm-hmm.
So you haven't gone through chapter 11 of
we have not.
Okay.
Not yet.
Didn't we skip from chapter 10 to chapter 14?
Yeah. We're gonna get back to it though, but we currently
get back to
skipped it.
that. So you push chapter 11 to later. All right. So that's a different order than mine. Actually, when I taught this, I put chapter 11 right away because that's the most fundamental things, complex analysis. So I taught it right away. But anyway, just so you need to accept my word if you are for the three of you. Okay, so just like a preview of what you learned for complex analysis. So let's just, so I'll go through a little faster because you haven't actually learned that method before. But what you need to do is substitute this into this G formula, this integral. And so that will be just using this into here. And we actually, because there's minus omega square in here, so we'll actually flip the sign and get this as a second order polynomial for omega, starting with omega square. So we'll get minus sign O. Okay, minus omega p square over 2 pi. And then we'll integrate. And so you have this e to the minus I omega tau and d omega. And so after you flip the sign, this is just a quadratic polynomial. So you can factor that out, just like solving a quadratic equation. You get two roots, and so you get factor this out as two terms, omega minus omega 1, omega minus omega 2. Okay, and this solution omega 1, 2 is very simple. It's just like solving a quadratic equation using the whatever minus b plus and minus square root of that kind of a formula. And using those, this form, you get the two root as this minus I omega plus and minus. The square root term is minus gamma squared plus 4 omega 0 square. This is square root. Okay, so that's that. And the integration is along omega, and so it's you draw it graphically along omega. So omega, this integration variable is wheel, so you draw it along the wheel axis of omega, but you extend it in a complex plane. So this imaginary omega. So this is wheel omega. This is imaginary omega, omega I. This omega R, which is just omega in this integration. This is the complex omega plane. Okay, And the denominator has two factors, and in complex variable, we say that you have two poles, and the two poles are at the location of omega 1, omega 2, which is at the location with imaginary part minus I or gamma, and then plus this one, assuming that this is a real part, so you have two poles, so-called pole. You have omega 1 and omega 2. Okay. So that's two poles, and they integrate along the wheel axis. Okay. All right, that's the setup of this integration. Now, to do an integration, to do this integration, first you notice there's the exponential factor here. And this exponential factor will allow us to close the integration by going a loop. So, and where do you go is you try to go close it like a big circle. You try to close it along a circle that so that the integration along the circle will be 0. And that depends on whether this exponential function will be infinitely small or infinitely large. And that depends on whether the real part of this argument is positive or negative. If it's positive, then it will be very large, then you cannot close that. So you need it to be negative. So when you close it along now it depends on the sign of tau. So if tau is negative, so negative times this minus sign become positive. So omega has a real part and imaginary part when you close it along a circle, semicircle. If omega has a positive omega I or the imaginary part, then like if you have this circle here, if you close it up to this circle, then omega I is positive. So I times I is negative. So the whole argument of the exponential function is negative. So the contribution from this big circle is 0. So you can close it there. And in complex integration, when you close it a loop, the integral depends on the contribution from the so-called residue, the pole, or inside this loop integration. Now there's no singularity. So this plus that equals 0, but this integration is 0. And so this integration along the wheel line, the wheel axis will be 0. Okay. So just by this form, and that the two poles actually is in the lower part of the complex plane, the lower half of the complex plane. So if omega I is negative, okay, that means for tau is greater than 0, tau is smaller than 0, G will be 0. So the first consequence is G tau smaller than 0 is exactly 0. Okay, so that's the consequence of this model of the dielectric constant with the two poles on the lower half of the complex omega plane. Then tau, when tau is smaller than 0, G is 0. So that's the one consequence. So for tau is positive, then you cannot close along this path. You have to close it the opposite way. So you close it in the lower half. Okay. Now, when you close in lower half, when tau is greater than 0, the contribution along this semicircle is still 0, but the whole loop integration will be summing over the contribution from these two poles, or to the two residue of these two poles. And then you can, that's a way to calculate the residue. And for a simple pole like this, very easy. It's 2 pi I times the residue. And for a simple pole, it's just multiplied by the same factor and substitute omega equals to the value of the pole. Okay. For that one, so you're summing over the two terms. Okay. And also the sign of this loop, if the loop is clockwise, you get a negative sign. anti-clockwise, you get a positive sign. Okay, so when I'm going through it quite quickly, so because I'm actually not in complex, not in math physics, but assuming you know, or you just take my word. So omega p squared, so copy this factor in front. So you get the residue, but for this is clockwise, so you have minus 2 pi I. Now you sum over the two residue. Okay, so for residue omega 1, you omega equals omega 1. And then you cancel the omega 1 term, cancel this term, and then this becomes omega 1 minus omega 2. And then you plus the contribution from the omega 2 residue. A residue of the omega 2 pole. And then you cancel this term, your omega 2 minus omega 1. Okay. And now the omega 1 and omega 2 are given by here. So the denominator is the same except the negative sign. So you basically subtract 1 to 2, and both are just exponential function. Okay, so you after you subtract that using this form, so what you get is I will skip all this algebra, but you just take my word for it. The add up of the two exponential functions for the imaginary argument, you get a sign over here, but then there's a real factor in the exponential function, you get minus gamma tau over 2. Okay, so that's the final form of this integration for tau greater than 0. For tau less than 0 is 0, so we can combine everything and write g tau is this one multiplied by a step function of tau. So only tau is greater than 0, you get this form. Okay, so that's g tau based on the physical model that we derived for the dielectric constant. All right. I know I'm going very fast, but anyway, any question based on that? Anyone want to me to go through even a little bit more? Then okay. If you haven't taken complex variable, this may be a little difficult. But if you have taken, you probably have will not have too much trouble, because that's just a formula that you use just using residual theorem. Okay, so that's this part. Okay, and that give you one idea why one idea of this the one idea of the g function. Now, if for the g function, after you do the integration, if tau is only non-zero and tau is positive, then this integration will means integrating instead of minus infinity into infinity, you're integrating 0 to infinity. So it means that the d would depend on E with tau is positive. So t minus something positive means in the past. So d only depends on electric field in the past from the evaluation time. Okay, so that is reasonable, because supposedly D should not depend on E in the future. It should only depend on E in the past. So that's what we call the causality condition. So it means that the physical model that we derived before have this epsilon as a function omega that make the G only positive, only non-zero for a positive tau, so that the D will only depends on electric field in the past. So this physical model of epsilon actually satisfies the causality condition. Okay, so of course, not all model will satisfy that. And we trace that the reason why it satisfy that, because we have this damping term. We have this minus I gamma. So you have a medium that has some physical damping that satisfies the reason that is actually the oxidation will damp in time. Then we satisfy this causality condition. If instead of gamma is not that it's not real damping, it's like an unphysical situation actually growing instead of damping, then you get the total reverse situation. Okay, so that will not satisfy the causality condition. So the model or physical model is important to satisfy the causality condition. And in the deeper reason is that this epsilon, the dielectric constant of a media, the media is a macroscopic physical system with many particles. So it must satisfy thermodynamics. So thermodynamics must satisfy, and so the thermodynamic consequence is that you satisfy the second law of thermodynamics. So that depends on the time, in a direction of time or the time arrow, so that will give you the causality. So it means that the present value depends only on the past value instead of the future value, because you don't know the future by the second law of the thermodynamics. So therefore, it must satisfy that. So when we build any model for the dielectric constant, it must satisfy this causality condition. Okay, and the consequence will be G is only non-zero for positive tau. Okay, so that is the condition. Okay. All right. Any question? Anyone?
Yeah, I think it makes sense.
It makes sense. Okay. Anyone has question? I mean, problems hearing me? So my internet seems like not very stable. Everyone can hear me?
I've been able to hear you. I don't think
Yeah.
anything's broken out in terms of
Okay,
audio. It's just
okay.
your video gets a little laggy.
Okay, so maybe that not very stable. Okay. All right, so this is the motivation for this discussion of causality. So now we can impose the condition for causality after this motivation. We basically impose the causality condition by saying that G must be zero for tau. G must be zero. Equals zero for tau is less than zero. And for the continuity condition, so we'll even say that when tau equals zero is also zero. Okay. So that's the consequence of the causality. So based on that, we can rewrite our previous integral condition as this one. You have E xt, the first term, and then plus this integration over G. But now we restrict out integration to positive tau. Okay, so that's the condition. All right. So all right. And now we can, this G tau is like the Fourier transform, right? So we can actually write this fact function -1. So G tau is like the you can it's like the express as Fourier transform using this function, right? So we can get this using the Fourier transform relation and get it's like a G tau e to the I omega tau and d tau. But since G is 0 for negative tau, so we just integrate from 0 to omega. Okay, so that give you the reverse relationship between epsilon, omega, and G. So basically, this is just a consequence of like the form of G that looks like a Fourier transform of this function. Okay, I mean it's inverse Fourier transform of this function. But anyway, this G by this relationship, because this relation is in the physical space in D and E and everything is real, so G is real. Okay, so that will give you a relationship or a constraint of this function that if you evaluate epsilon omega as minus omega in the dielectric constant function, so we can now change this omega to minus omega, okay, and then we can write like because G is real, we can write like the same thing, but take the I omega tau and take the complex conjugate. So this minus omega, at first you get a minus sign in here, but then you take the complex conjugate, change I to minus I, so you get that. But then omega, we actually will extend the complex spring, so we take the complex conjugate of omega also. Okay, and now just by this form is exactly as this form, so this thing is just the whole thing inside the bracket is just this one, evaluate omega complex conjugate, and then you take another complex conjugate. So that becomes epsilon complex conjugate, evaluate omega complex conjugate divided by epsilon 0 minus 1. Or simplify it, epsilon at minus omega is epsilon complex conjugate at omega complex conjugate. Okay, so that's the constraint of a dielectric constant as a function of omega. Satisfy this relationship. Okay, so and that has a consequence of this one has a consequence of the complex function, the structure of this function on the complex plane, because we require this G that is 0 for tau is negative. Okay, so it means that this is epsilon, right? So if you evaluate epsilon on the complex plane and you do this integration, and for just like what we had before, if you draw a complex plane of omega, so omega I and omega R, okay? So for omega within the upper plane where omega I is positive, then this exponential function omega I is positive, right? So you have I times I is negative, and you integration over positive tau, so that one is finite. When you integrate tau from 0 to infinity, because that exponential function we have a negative argument when you integrate, so that's epsilon. will be finite. It will not get singular value. So it's fully finite. So this analytic within this plane. So epsilon is analytic over the upper plane. Epsilon analytic. If you haven't learned the concept and analytic functions, or probably you just take my word. So it means that epsilon will not be singular over this plane. So all the singularity of epsilon or the poles that we talk about must be occurring in the lower plane. That's just exactly what we saw from the physical model we just did. In the previous model, we have 2 poles on the lower plane, but there's no poles, no singularity on the upper plane. And that is you can get that from this relationship also, right? So, and from this, you can also extend it to when omega is real also. But then this integration will require that the G will goes to 0 at tau goes to infinity. That will work for dielectric medium, but for matter, actually there's one singularity in this epsilon. Actually, we'll have a real omega. There will be one of omega term for the dielectric constant. That actually we see that from matter. So other than that, there's no singularity on this upper plane. Okay, so we have just a few minutes left. So any question up to here? Okay, so the next topic is, because finally we'll derive a very important relationship, so-called Kramers-Kronig relation. And that derivation also need complex analysis, but that actually requires some preliminary structure. So we actually need to know what epsilon omega is when omega getting large value. So to do that, we need to get the so-called asymptotic relationship or asymptotic property of epsilon. So we can think about this function. This is given by this one, but we can rewrite this one as another form and do integration by parts. Because it's an exponential function, we can think about it as a dd of tau of this one, because when you take the dd tau, take the derivative with respect to tau, you power I omega, so you can divide it by I omega here, and then d tau. So that will allow you to do an integration by parts. So that will give you the first term. The first term will be just, oopsie. Okay, so just the G at 0, because assuming G is 0 at infinity, so we don't have the infinity contribution. And we just evaluate this as 0. So this will be G as 0. And this is in the lower half, so a minus sign, but you can flip the I over here. So the first term is like that. And that becomes I omega. And then do the integration. And that one is dg d tau multiplied by e did I omega tau d tau. Okay, so all right, so this one is exactly the same form as the original one, as this one. So we can keep doing this integration by part process. So then the first one will be just what we had before. The second one will be I omega, and then multiplied by I g. instead of omega, if the G evaluate 0, you have G pi or d tau evaluate 0 and divided by another omega and so on and so forth. So you can keep doing that, right? And that will give you the asymptotic expansion of epsilon for large omega. And one more thing we'll use is that when tau is 0, we actually require G tau to be 0. So the first term actually is 0. So the leading order term is 1 over omega squared, and it's real because G is real, G pi is real, and I times I is -1. So the first term is minus I minus G pi 0 divided by omega squared. All right, and the third term will be actually have another I here, so you have a 3I, right? So what you get is an I times omega double pi. Let's see, you have I times, right? So you have a minus I over omega q G double pi 0. So the real part will be the first term, the imaginary part. The real part will have 1 over omega squared. The imaginary part will be the leading order 1 over omega cube. Okay, but both will go to 0 at G is large. And we'll use that to derive the Kramers-Kronig relation, which we'll do it on Wednesday. Okay, so last time we stopped at here. So this is the function that dielectric constant on relative dielectric constant -1. So that's function. We can get the asymptotic expansion, which is the inverse power in the argument, so omega. So, and by integration by part, we get to this at least the first couple of terms. There are more terms, right? So you see that by continuing the integration by part, repeating the integration by part, you will get the even power of omega, inverse power of omega. The even terms are all real. The complex, the imaginary terms are all odd in omega. Okay, so but the most important part that we'll use is that this function, as omega goes to infinity, is at least decaying as omega square, 1 over omega square. So it goes to 0, but you need to know how fast it goes to 0, and it's the at least as fast as 1 over omega square. So that's the property that we'll use. Okay, and then another property of this epsilon function is you will see that we'll probably talk a little bit more. So the real part of epsilon is all even function in omega. The imaginary part of epsilon is odd function in omega. So we can see that from here too. Okay. We'll also use that, but there's another way to see that. We'll see that in a moment. So now we get to the main part of this section, which is to derive the Kramers-Kronig relation, which is very non-trivial, and it's not just for E and M. There's other system that has similar relation. So because it's basically a general mathematical result. Okay, so so now we basically established that in the omega complex plane, this is real omega and imaginary omega. Okay, so we established that epsilon as a function of omega, we extend that to complex omega. All the singularities should be on the lower half of the complex plane. So you could have singularity of epsilon below the wheel axis. Above the wheel axis, the whole function is analytic, or we actually consider this function the relative dielectric constant and subtract by 1. So these are all functions, so it doesn't change the property of whether it's analytic or not. So this function is analytic over the upper half of this complex spring. And then last result also showed that it's going to 0 as fast as 1/omega squared. When omega goes to infinity, the magnitude of omega goes to infinity. Okay, so now we'll apply the so-called Cauchy theorem. The Cauchy theorem will say that any complex function can be expressed as a loop integral of the function itself, and we'll use the another integration variable, say omega pi, divided by epsilon 0 minus 1. So basically the same function, and you do the integration over the loop integration over a path with omega pi minus omega. Okay, so this is a function omega. This is a function omega pi. You integrate over omega pi, but you divide it by omega pi by omega. So this is called a Cauchy theorem. And the requirement for the Cauchy theorem is that this loop integral, this path, the whole function is analytic within this path. So that's the main idea. If the whole function has no singularity, or is analytic over the whole interior of this path, this loop integration, then you get this result. So omega is within the C, and we'll choose the path as so part of the path is the wheel axis. We integrate along the wheel axis, and then we close the path by going to infinity, a semi-circle at infinity. Okay, so this is our C. This will be our path. So integrate like that, all right? And we have established that this function is analytic over the inside the loop because it's in the upper plane. There's no singularity of epsilon. So we can use the Cauchy theorem for any omega within this loop. This is a valid result. Okay, so this is called the Cauchy theorem. So it applied to complex function, so not just E and M. So you can use that for other situation. Now the idea now is so you choose any omega. So this apply to any omega within this loop, but then what we will do is move this omega, consider omega going down and approaching the wheel axis. Okay, so finally we'll actually move the omega to right on the wheel axis with just a infinitesimal positive imaginary value. So what we'll do is like that. So we let omega, actually we could, because now I'm using a limiting situation, so I could change this integration, we call this Z instead of omega, because Z is just a complex value. And then letting C, consider C going to omega as a real value, plus a small imaginary part. This is a plus. Okay, and then with delta going to a positive infinitesimal value. Okay, so we'll do that. Not any value. So this will be what we call Z. And then my let Z goes to omega as a real value plus an I delta. Okay. All right. So then I'll rewrite this result. So basically, I'm writing epsilon. Now, because delta is so small, I can just say that this is just exactly like omega. And then this is equals to limit of delta going to 0 plus. I forgot to, in the Cauchy theorem, you need to divide it by 2 pi I. I forgot. So this divided by 2 pi I is this function. Okay. And then 1 over 2 pi I. Now the integration becomes, because if a delta is so small, we're saying that the integration is like just integrating omega prime over the real axis. And because the contribution from the semicircle when the omega goes to infinity, this path doesn't contribute because this function, we have established that this function is at least goes to 0 as fast as 1 over omega square. Okay, so that's 1 over omega square here. And then you integrate along this path. So this is integration along the path will give you order omega, and then you still have a 1 over omega here. So the whole thing after integration is still decay as 1 over omega square when omega goes to infinity. So the integration along this semicircle is 0. Okay, so we don't need that part. So you just need the integration along the real axis. That becomes omega pi minus omega minus I delta. Just substitute z equals to this one into here. Okay. All right, so that's just taking the limit of any interior point and let it approach the real axis, and we get to this result. Okay, now we are going to use another formula. So this function 1 over omega pi minus omega minus I delta, as delta goes to infinity, going to 0, delta goes to 0 plus. Okay, that one will be equals to the principal part of 1 over omega pi minus omega plus pi I times delta function omega pi over omega minus omega. Okay, I don't know whether you have seen this before. Anyone have seen this relation before? Have you seen that? Have you seen that somewhere? It probably will be used in some other situation like quantum mechanics.
I don't think I've seen that.
You'd have seen it before. So the notation here, this P, capital P is called the principal value or principal part. So the delta function as well as this P is only meaningful if you put it in under integration. So both are interpreted as something that you use after you use it, you need to do an integration before you. That makes sense. And when you put the right-hand side in the integram and do the integration, this capital P means that you are doing an integration without including this singular point. The singular point is that when omega pi equals omega, say like right at here, the real value of this integration variable is omega, and you integrate along omega pi along this axis. And this principal part means that you integrate very close to this singularity. So, and then you ignore a certain distance. Let's give it a symbol. we have already used delta and epsilon. So what symbols I use? Like what is? Let's see, just nu, small number. So you stop at nu before this this singularity, and you call it nu as whatever, nu as positive value, and you resume the integration at the same distance, nu, across the singularity, and resume this integration. So this integration up to a certain distance before the singularity, and resume the integration after this singularity. This is important. You have to use exactly the same distance, and they resume the integration to infinity, and nu, and let nu goes to 0, 0 plus. Okay, and that integration is called the principal part or principal value of this integration. Okay, so you basically, because you have a singularity, you just ignore that and integrate over the singularity, you get infinity, and that's or something undefined, and that's not good. But once you define your way to integrate it, that this principal value can give you a finite result. Okay, so that's the trick. And then the delta function, you know that we talk about delta function, and you can get this in a few lines of in the derivation, but we won't go to that. There's a name for this relation. This is so-called. Let me just write it down for you. This is the name is kind of a little bit difficult to pronounce. Promote formula, something like that. Okay, and it has different forms. So this is one way to express that under our context. It's like that. So this, you can use this promote formula. Now you can to evaluate this integral. Okay, does it make sense? This relation? If you haven't seen that before, you just need to accept my word that this is true. So this is one of the mathematical relation that you can use. All right.
Could we see a more concrete example?
We'll do an integration after we derive the Kramers-Kronig relation. Okay. We have an example for that, but we'll do that. I don't know whether that will answer your question. Ask me after that whether you after the example whether it's clear or not. Okay, so if you haven't seen this kind of notation before, that might be a little bit confusing. But
I thought we saw this notation in math physics with you.
yeah, so when we talk about complex variable, we probably talk about principal value before. Okay, so, and by the way, the different notation for the principal value. Some people will use principal value or principal part, so or something like that. So they're different notation, but they're talking about the same thing. Okay, so and now after you do that and use this promote formula, you can evaluate this at least formally. And because this is one equation with both real and imaginary part, because assuming epsilon can be is a complex function, can have real or imaginary part, although omega will treat omega as real, but still the function epsilon itself can be complex. So this complex relation have both the real part and imaginary part. Okay, and this is exactly the same function here. This function and this function in the integram is exactly the same function. And then we are dividing by 1/2 pi I, so there's an I here. After you put these two terms, this term we only pick up the real part. So this part, the principal part will be real after you do the integration, but then divided by I, okay? So this part is real. So if you have take the imaginary part will cancel the I, and this is real, then you will get the real part for this function. So the real part is related to imaginary part of this one, using this term. Okay, so I probably should, well, there's one more line of integrate because there's two terms. Let's simplify that after you put it into here first before we talk about that. Actually, it turns out that both terms will give you similar contribution. Let's just put that and do the evaluate that explicitly first. So after you substitute this into here, then so there's a there will be two terms, and now you already let delta goes to 0 using this relationship, so you don't need to carry this limit anymore. So now there are two terms. One is the principal part of evaluating this function. Okay, and divided by omega pi minus omega. So that's this part, this going to here. Okay, so then the other part is pi I, so you cancel this pi I, right? And then you do the integration. Well, I mean, we will include it in the bracket, so you keep the pi I first. And then the delta function will give you just omega pi and change to omega. So you basically copy the same function. Epsilon omega divided epsilon 0 minus 1. Okay. But this is just using this formula and get it in the denominator and evaluate that, and you write it like that. Now you see that the left-hand side and the second term of the right-hand side is exactly the same, because after you cancel this pi I, this is a pi I, except that the right-hand side is just half of that. So the second term on the right-hand side is half of the function on the left-hand side. So you can subtract this half from the left-hand side. So left-hand side becomes a half. So you keep that, and then the left-hand side you just have the first term. Okay, and because it's 1/2, so the whole thing is equals to 2 times the first term. Okay, so you move that to the other, subtract that, you get half of this one. So you only have the first term on the right. So you multiply this half, multiply 2 by 2, and cancel this. So this function will be 2 times of the first term. So you can write it just 2 times of that. So pi I, principal part of the same function. Okay, now we get rid of the delta function. So this is equals to just that. Now we can go back to our discussion. So the real part of this one will relate to the imaginary part of this one, the same function. And because there's an I here, and likewise, the imaginary part of this function, the left-hand side will be related to the real part of this function, because the real part will make the whole integral real, but you are divided by I, so the whole thing is imaginary. Okay, due to the real part. Okay, so that would be the imaginary part. Okay, so what you get from this complex equation is the relationship between the real part and imaginary part of this function. So the real part of this function will be related to the imaginary part of this function. The imaginary part will have, the imaginary part plus I, then you cancel I, so you have just 1 over pi of the principal part of the integration of the imaginary part of that function. And when you take the imaginary part, you can take only the first term because the second term is 1, so that's a real. So then divided by omega pi minus omega. Okay, so the first relation is this one. And you can do the same thing with the imaginary part. Imaginary part of, again, you keep just the first term. That will be equals to the real part of that. But then this is divided by I, so you have a minus sign because you flip the I to the numerator, you get a negative sign, so that equals the negative 1 over pi principal part of the real part of this function divided by omega pi minus omega. Okay, so that's omega pi. Okay, these two are what we call the Kramers-Kronig relations. Okay, so finally we get what we want. There's another form, we'll get to that in a moment. But this is a perfectly valid form for the relation that we want. Okay. All right, so this is the final relation. Any question about this derivation before we talk a little bit more about this? What the reason? This is highly non-trivial property based on this relation. We'll talk about that in a moment. But for derivation, is it okay for everyone? Yeah, at least you know the steps. You need to, if you haven't seen this before, you need to accept this formula. And also, if you don't know complex variable, you need to accept this Cauchy theorem. Okay, but after that, that would be the consequence. I mean, this complex variable is not that difficult. The Cauchy theorem is, a few sections into the complex variable chapter, you'll get to that. Right, so it's very basic theorem in complex variable functions. Okay, so, but the consequence is quite non-trivial, because what it's saying is that for a dielectric constant that depends on frequency, so you cannot have so for the first, like you look at the first equation, because we know that the imaginary part of epsilon is corresponding to absorption of the medium. So what this relation saying is that for a medium that has absolutely no absorption, so over the all frequency, if you assume that there's a medium that does not absorb any electromagnetic wave, for all frequency of the wave, the absorption is absolutely 0. So it means that the imaginary part of epsilon is absolutely 0. Then after you do the integration, the right-hand side will be 0. Then it related to the left-hand side means that this epsilon must equals epsilon 0. So, which means that the medium is exactly like vacuum. So the only medium that has absolutely no absorption over all frequency is the vacuum. Okay, so this is the consequence of this one, the first relation.
So
Okay.
just a question about what you said. You said that the epsilon of omega must equal 0, but isn't that, am I reading this correct when I says the real of epsilon omega over epsilon naught minus 1?
Yeah, this one must be equal to 0.
Oh,
So
okay,
epsilon over epsilon 0 minus 1 must be 0. So epsilon must equal to epsilon 0. If,
okay.
if
I missed-
epsilon is absolutely real and no imaginary part, so
right.
the left-hand side or the right-hand side will be absolute 0. So the
Mhm.
left-hand side will also be 0. So epsilon must always be equal to epsilon 0, which is just the
Okay.
vacuum value.
Okay, that makes sense. Thank you.
Okay, yeah. So you cannot have any a medium that is absolutely no absorption that is not the just like the vacuum. Okay, so that is the first consequence. Okay, and the second equation you can just the same thing, just talk about it in the reverse sense. So it's saying that if the real part of the medium is always equals to epsilon 0, and after you do the integration, it must be equal to 0, the right-hand side. It means that the imaginary part must also be 0. So you cannot have a medium with real part just like the vacuum value, but with absorption. With absorption must also be exactly 0. So that's go back to the vacuum also. Okay, so these two relations are related to each other, but you need both of them because that's the two parts, the real part and the imaginary part of the same equation. Okay, so that's one of the highly non-trivial result because before you have this result, or before you actually going through the derivation and get these two equations, you won't get that. So you will see, you will expect that anything is possible. So a medium can be totally without absorption, but then the dielectric constant will be different from epsilon 0, or the refractive index is different from 1. You probably would expect that, but by this derivation, you see that that is actually impossible. And you trace back the argument, you realize that this is a consequence of the causality argument. This is totally due to the causality. Okay, so so the part of the argument of causality actually quite powerful because it's allowed you to derive a very non-trivial result. Okay, so that is the Kramers-Kronig relation. Okay, so this is one form of writing it. Then another form to write this is to use the symmetric property of this epsilon, because we already talked about that the real part of epsilon is even function in omega, and the imaginary part is odd function. We can also see that from the relation that we talked about last time. So if you evaluate epsilon at minus omega is the same as evaluate the complex conjugate of epsilon evaluate at the complex conjugate of omega. Okay. Now, so this is valid for any complex omega, but if you choose omega as real, then and you take the real part of that, real part of epsilon minus omega for real omega, that will be, because you are taking the real part of both sides. When you take the complex conjugate of a function and you just take the real part, so it doesn't change because it's just the same. So it will be just the real part of epsilon and evaluate at the same omega because you assume omega is real. So you see that the real part is symmetric between omega. So omega changes minus omega, the real part doesn't change. So epsilon is an even function of omega. And you can do the same thing as the imaginary part of epsilon minus omega. When you take the imaginary part of a complex conjugate, you get a negative sign. So negative sign of imaginary part of epsilon omega. So this means that the omega part, the imaginary part of epsilon is an odd function of omega. So this means is involve all the odd power. If you do a power expansion, it will involve only the odd power of omega. Okay, so now then you can because this integration in the original relations is integrating over minus infinity to infinity, so you can write it out two parts of minus infinity to 0 and 0 to infinity, and you change the integration variable minus infinity to 0 with the negative of the integration variable. So you change that to integrate from 0 to infinity again, but with the argument, all the epsilon will depends on minus omega, just like here. But then you use these two relations to flip the sign, and you also flip the sign of the integram also of the omega pi for that first term, and you combine the two terms, and you can write the same thing in as integral to over just integrating over 0 to infinity. So that's another way to write it. And after you do all the algebra, I won't go through that. In my notes, you can see the details, but just to save some time, let's just write it out. That's in your textbook also. Okay, so we can write out explicitly. So that's the alternative form of this relationship. Will part of epsilon over epsilon 0 minus 1 equals to 2 principal part, so 2 pi. Integrate, now it's just from 0 to infinity, and you have omega pi, and the imaginary part of epsilon over evaluate omega pi divided by epsilon 0 divided by omega pi square minus omega square, integrate over omega pi. Okay, so that's the first equation, and the second equation, and do the same thing. This is equals to minus 2 omega over pi principal part, integrate 0 to infinity, and the real part of this function, epsilon omega pi over omega over epsilon 0 minus 1 d omega pi divided by omega pi square minus omega square. Okay, so these two are exactly the same as the last one after you use the symmetric property of epsilon with respect to the argument. Okay, so both are the same, so it doesn't matter. All right, so to derive these two from the first set is quite straightforward, so I won't go through it here. Okay,